Hello, everyone. We are Team 2. Our project is blockchain-based authentication for IoT for cloud environments. I'm Anuradha.
I am Yao Isaac.
I'm Liu Jiangyuan.
And today we will discuss about our project.
Okay, so the first point of our project is about the problem that our tool aims to solve. First thing we should be knowing is that IoT is a network of devices that are embedded with software and sensor to connect to exchange data with other devices and systems over internet. Security systems remain the biggest concern in IoT devices, as they are highly vulnerable to attacks. Authentication is one of the main IoT security concerns. For example, IoT devices need to communicate with each other and share data among themselves. Many types of attacks are possible on IoT authentication. We have, for example, the masquerade attack, man-in-the-middle attack, DOS attack, foraging attack, guessing attack, and routing attack. Next slide, please. Now we are going to discuss why is it a problem. Security was never thought in a design or development stage of many of the IoT devices. Many of the network and protocols that connect to them don't have a robust end-to-end mechanism. Due to the limited memory and processing power, IoT devices lack robust security solution and encryption protocols. The traditional security solutions are not fully adapted to IoT environments because of limited resources and heterogeneous devices. And finally, existing efficient security solutions are centralized, which can cause scalability issues in IoT networks. Next slide, please.
How severe is the problem? This slide shows the OWASP's top 3 problems of IoT. And the first problem is weak guessable or hard-coded passwords. And the second one is insecure network services. And the third one is insecure ecosystem interfaces. Next slide, please. And how severe is the problem? The first one is the Maria botnet. The largest server DDoS attacks on service provider DNS crypto website in North America and Europe in 2016. Once infected with Maria, computers continually search in the internet for vulnerable IoT devices and then use known defaulted usernames and passwords to log in, interfacting them with malware. More variants of Maria have come up since the source code was released. And securing IoT devices is not only important for data security of enterprise, but also for crucial entities such as human lives and national intelligence. A vulnerability discovered in 2017 in Peacemaker devices lead to the recall of 500,000 pacemakers by U.S. Food and Drug Administrations. The vulnerability could cause a hacker to control the heartbeat of regulation devices. And for our project goal, the first one is create a secure identity verification mechanism for IoT devices and perform security authentication for devices to be connected to the IoT system. The second one is the decentralization and encryption properties of blockchain technology can be used to create a secure identity verification mechanism for IoT devices. The blockchain uses encryption technology to ensure that data cannot be tampered with forked. It can safely store a priority and verifiable safely data information. And the third one is proposing a blockchain-based decentralized authentication mechanism for IoT devices. And the last one is implement and test a prototype for the proposal solutions. Next slide, please.
Okay, what we must know about in order to understand the tool. The first thing is the blockchain. a list of cryptographically linked blocks. And the second thing is the fog computing. Should be knowing that it is a decentralized computing infrastructure in which computing resources are located between the data source and the cloud or any other data center. Next slide. Okay, as a literature review that support our research, we have this first one that talk about managing IoT devices using blockchain platform, written by SU and allies in 2017. They created a management system to control the integrated devices like light bulb and air conditioner using Raspberry Pis and the smartphone that was used to enter the data sent to the Ethereum network. One of the shortcomings that this project registered was the transaction time that was of 12 seconds, which was kind of slow for a system that require that are time related, that have time related issue. Thank you. Next slide.
For the second literary review, the project was talking about the cloud-based IoT devices authentication sketch using the blockchain. And the author was the K. Albert Y and was published at 2019. For this article, is saying the author team was aimed to use blockchain to develop a cloud-based authentication scheme for IoT devices to overcome the disadvantage of high cost or long verification time brought by shortage and processing capabilities. But for the shortcoming, the SketchMe they set up has like if there are more devices was joined, the longer the devices registration time and the authentication time that it will be have, and the easier is for an attacker to attack encrypt devices against the leakage of size channel information during the operation of the device. Next slide, please.
This is the third literature review that we did. It was a paper proposed by Khalid and team. These authors, they proposed a decentralized authentication and access control mechanism for IoT devices. And for their proposed solution, they used a smart hospital as a case study. One of the shortcomings of their work was that they used Ethereum blockchain, and which takes a minimum of around 14 seconds to complete a transaction. And that may add an additional delay to their proposed authentication mechanism. Now let's see like what our tool is and how it works. So this is the system overview of our proposed solution. We have two layers. One is the IoT layer and the other is the FUG layer. The IoT layer consists of IoT devices that are trying to authenticate themselves. The FUG layer consists of a number of FUG nodes. The FUG nodes, they add the processing capabilities and reduce the latency and response time for IoT to cloud interactions. So the FUG layer adds improves the performance of the overall system. In our proposed system, the FUG layer is used to run the blockchain. So all the FUG nodes are part of the blockchain network. The IoT devices, they need to interact with the FUG nodes for authentication purposes, for authentication and registration purposes. Our software solution has two parts. One of the Python program is running on IoT devices. And this code handles like creating the public-private key pair. We are using RSA for that. Sending requests to the FUG nodes for registration and authentication. And decrypting the encrypted message it receives from the FUG nodes. The other program runs on the FUG nodes. That code handles the blockchain, the functioning of the blockchain, like creating the blockchain, doing the device registration and authentication based on blockchain. There are two types of communications here. One is IoT device to FUG node, and one is between the FUG nodes. So the IoT devices need to interact with or communicate with the FUG nodes for registration and authentication purposes. And the fug nodes, they need to communicate with each other for synchronization of data. There are two phases of the operations here. One is the registration phase and the other is the authentication phase. So in the registration phase, when an IoT device initializes and tries to enter a network, it generates, during initialization, it generates its public-private key pair using RSA public key crypto system. Then it contacts the nearest fug node for registration. For registration purpose, during the registration request, it sends the MAC address and its public key to the fug node. When the fug node receives the registration request from the IoT device, it uses the MAC address and the public key of the device and creates a new block and add that block to the blockchain. After adding it, it successfully registers the IoT device and sends a registration successful back to it. Along with that, it also sends a message to IoT device, an encrypted message. And that encrypted message, it encrypts by using the IoT device public key, which it obtained earlier. So the IoT device decrypts the message using its private key because only it has the corresponding private key, so it can decrypt the message. In the authentication phase, like we have two scenarios. One is, in the first scenario, we have like an IoT device sends an authentication request. After successful registration, the IoT device sends an authentication request to the same fug node on which it registered itself. And the second scenario for authentication is like the IoT device is it registered itself with a fug node, but it moves to a different, which is, and in that location, the nearest fug node is a different one. And it tries to authenticate itself to that fug node. So it should be able to authenticate itself to that node as well, because both the nodes are, or those nodes, fug nodes, are part of the same blockchain network. So the sequence of events is like the IoT device sends authentication request to the fug node. And in that authentication request, it sends its MAC, its ID, which is the MAC address. The fug node checks the IoT device ID in the blockchain. And if it exists in the blockchain, it sends an authentication success to the IoT device. And along with the authentication success, it also sends an encrypted message similar to the registration request, encrypted using the IoT device public key. And when the IoT device receives that message and authentication success, it decrypts the message using its private key. If the fug node does not find the IoT device in the blockchain, it means the IoT device is not registered in the blockchain with any of the fug nodes that are part of the blockchain network. So an authentication failure is returned in that case. This is the sequence diagram of the two phases, the registration phase and the authentication phase. RP1 shown here is the IoT device, and the other one is the fug node. So the first event will be RP1 sends a registration request with its ID and public key. The fug node saves it, creates a new block, adds that block to the blockchain, sends a registration success or failure message, sends the encrypted message. These things we have seen in previous slides. So then when it receives the encrypted message, RP1 decrypts the message and shows it. For the authentication phase, RP1 sends a request with its ID. The fug node checks the blockchain. If found, it sends the authentication success. And it also takes the RP1's public key, which is stored in the blockchain, in the block in the blockchain. And it uses that public key and encrypts the message and sends the encrypted message back. There were some key design decisions which we took while we were working on the project. The first one was the choice of the language. We chose Python to be our programming language. We decided to use private blockchain rather than using Ethereum or Bitcoin. And we decided to use public-private key pair for authentication mechanisms for more security. The reason behind those decisions was like we wanted to create a code which is easy to understand, and we wanted to make the code more generic. To evaluate our tool, there are two scenarios that should be tested. The first scenario is the IoT device should be able to successfully register itself to the nearest fug node. And after successful registration, the IoT device should be successfully authenticated to the same fug node. And the second scenario is IoT device can successfully register itself to one fug node, and it moves to a different location managed by a different fug node, and it can successfully authenticate itself there also with the other fug node. To show the evaluation results, we want to give a demo. So for the demo, our setup is this. We have three nodes or three VMs, we can say, FRP1, FRP2, and IoT RP1. FRP1 is acting as our fug node 1, FRP2 is acting as our fug node 2, and IoT RP1 is acting as our IoT device. So we have this, this is the fug node, which is listening, and a device. This is the IoT node. This device sends a request to that fug node for registration and authentication. We are testing the first scenario here. So, okay, let's see the sequence or the logs here, which are generated. So this one, the device registration server listening, it got, the fug node got the device connection. It started the IoT device registration process. In the registration request, it got the MAC address of the device ID here. After getting the MAC address, it saves it into unconfirmed devices and then mine the and create a block for it. Then it mines the block containing the new device information with this device ID, created the block. The first block is the Genesis block, which we are creating with 0 values, null values. Then it added the new block to the blockchain. And these are the two IoT blockchain, the IoT devices in the blockchain. And it sends an IoT device registration successful. And it sends a encrypted message, this one, to the IoT device back. And then after registration, it got a request from the device again for authentication this time. Then it started the IoT device authentication, received authentication request. It checks the blockchain. It checks the blockchain for the details, whether it has the device ID or not. It returns a success, and it fetches the private key, the public key. It fetches the public key of that IoT device, which is stored in the blockchain. And it sends the current node. It found the device on the current node and successful, and sent the encrypted message. So these were the events which happened on the fug node. Now let's see what happened on the device side, like the IoT node. So it called the device registration function with its ID. It successfully connected to the fug node, and then it received the message from the fug node that normal registration successful. Along with it, it received an encrypted message, this one. It used its private key and decrypted the message, which is this one. Hello, IA693. We had fun learning and creating blockchain. And this is the length of the this message. In the authentication, during the authentication process, it connects again to the fug node, and it receives an ACK, means like a successful authentication, and along with the encrypted message. The message is the same. We use the same message to send it. And so this successfully authenticated it successfully got registered and authenticated to the same fug node, which is here. Okay. So this is the first scenario which we have seen. What we have seen now was the first scenario. Now let's see what happens if it moves to a different location and tries to authenticate itself to a different fug node. For that, we need to, because for POC purpose, we wrote the code. So we need to change a small thing over here. Okay. So now we are saying that this FUG node, this IoT device will send the registration request to this node. And after successful registration, it sends the authentication request to this one. So it does not have the, it did not register with this one, but it should be able, even then, it should be able to authenticate itself successfully with this one, because these two nodes are synchronized and they can talk to each other and find the device information. So let's run. This is our first node. This is our second node. They both are up and running. And now we send a request to the FUG nodes. We can see that it registered itself, but it's not authenticating with this device. It's authenticating over here with the second FUG node. Okay, so yes, it got registration successful and authentication successful. Now let's see what happened on both of the FUG nodes. So it received this FUG node, FRP1, it received the registration request, device connected, and then it started the registration process. The same sequence of event happened, which we have seen in previous scenario. Device ID, blockchain, it created, registered successfully, sent the encrypted message to the device. And then these logs are different from the previous one because the request from the device then went to the second FUG node. So these are like, it will check in blockchain network. These three, don't worry about these three because I added them for logging purpose. I was testing something. So this over here, it checks the device ID. It got the IoT device authentication request. It did not, because it tries to check in its blockchain. When it did not find it, because it was not registered with this node, it searches its peers of the blockchain network if they have the information of this blockchain. So it sends the device ID to them, and it received an authentication successful along with the public key. That node sent the public key also to this node, and then it said device is successful, but it not from the current node, from a peer node, and successful status, and use that public key to encrypt the message and send the encrypted message. On the first FUG node, we can see that it received a message from the peer, got blockchain connection. It got a connection from the peer, and it searched its blockchain data, the blocks, and it received it, found it, and then it sends that okay, device found positive in the current node of this blockchain, and sent this to the FRP2. On the device side, the authentication and success, like it does not matter. The sequence will be the same. The device will not come to know, okay, what are the things that happened between the two FUG nodes on like the FUG layer. And it received like registration successful and authentication successful, same way. And these are the same results we have pasted here, which we have just seen. Second scenario. Yeah.
Okay. Now, in our discussion part while making the research, some points have been mentioned. For example, identity verification based on public key infrastructure avoid the cumbersome key distribution, key leakage, and large amount of calculation. Second point is that creating our own blockchain using Python made our code generic and easy to understand. The final point was, in future, we will work on connecting the fog layer to the cloud. Next slide, please.
So here is our group's conclusion, and there are 4 points. The traditional centralized authentication mechanism in IoT devices have security issues. The decentralized and cryptographic properties of the blockchain technology can be used to create a secure authentication mechanism for IoT devices. Propose a blockchain-based decentralized authentication mechanism for IoT devices, and a prototype was implemented to show the flexibility of the proposed solutions. Next slide, please. Here are our reference, and thanks for listening our presentation. If you have any questions, please contact us by phone or email.
Thank you.
Thank
Thank
you.
you.